Alright, this is going to be our last section. It's called Anova, A-N-O-V-A. This corresponds to chapter 13. Chapter 13. Anova is used to test the equality of three or more means. So what we're going to do here is, well, before we tested for one population mean, then we also tested for two population means where we're comparing if one is higher or they're equal. Now we try to compare three or more population means. We will assume that we have three or more samples, that each of the samples come from populations that are normally distributed. This one has a little bit more restrictions. So this is kind of theoretical. The three conditions are pretty theoretical. We want the population to be normal. Each of the samples are independent. That means they are not matched pairs. And the variances, or the standard deviations, of the populations are approximately equal to each other. Number one says, why don't we run two population tests? Mu1 is equal to mu2, mu2 is equal to mu3, and the mu1 is equal to mu3, to whether they're all equal to each other. There is like kind of short answer and the long answer. Short answer is each time we do hypothesis test, we have some chance of making an error. So when we do it three times, basically we are compounding. Chance of making error. And another reason is that suppose we have like 4 or 5 populations, then there are just a lot to test. Let's say I have 4 populations, then I have to compare mu1, mu2, mu2, mu3, mu3, mu4. But not only that, like I have to compare mu1, mu3, mu2, mu4. So more population means a lot more testings. So the Anova test gives you a nice way to test to see if all the populations are equal to each other in one shot. All right. So Anova, what this is, Anova step is A-N-O-V-A, stands for analysis of variance. Remember, variance is just standard deviation squared. So variance basically has the same property as standard deviation, pretty much. Number 2, draw a picture to illustrating the basic idea of Anova. So when we do this Anova test, we're going to use a calculator to do it, but underlying principle is basically what we're going to do is we're going to kind of look at, let's say I have population mu1, mu2, mu3. Like in terms of confidence interval, let's say mu1 is like this, confidence interval mu2 is like this, mu3 is like this, right? So what could possibly happen is there's a little bit of area where it could be in mu1, it could be mu2, it could be mu3. So there's a slight chance that they all could have a same mean because 3 confidence interval kind of overlap. If I look at another picture, kind of similar picture, but let's say we have now less variance or less standard deviation. That means your margin of error is going to be smaller. So we'll have similar confidence intervals, but like shorter, right? Like this. So the location is pretty much same, but their length of the confidence interval is now shorter. So shorter versus before. So in that case, it's hard to have overlapping point where all 3 confidence interval is contained, which is kind of not possible in this picture. So like here, this line includes the mu2 and mu3, but not mu1. Like this line may include mu1 and mu2, but not mu3. So I can't not find a place where all 3 confidence interval overlap. That means it's going to be hard to have all the means equal to each other. So basically, this test will see if we have some case like this where it's possible to have 3 confidence interval overlapping. So maybe it's possible to have all have the same mean, or it's not possible that they have the same mean. That's why we're kind of analyzing the variance, which is standard deviation, because that determines the length of the confidence interval. All right, let's look at the next part here. For Anova, the null hypothesis, H naught is always, it's going to be H naught is going to be mu1 is equal to mu2 is equal to mu3 equal to dot 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 mu whatever, let's say mu k. So if you have 7, then it's until 7. If you have 3, then it's 1 to 3. And the alternative hypothesis, HA, means at least one is different. So null hypothesis that they're all equal, the means are all equal. So here, right, all the means are equal. So null means all the means are equal. Alternative is at least one pair they're not equal. All right. So to test this, we're going to use the Anova function key, and what it uses is not normal distribution, not chi-square, but something different. It's called F ratio or F distribution. I'm not going to really talk about too much of a F ratio. It goes through like all the details of F ratio. So I'll kind of skip all the way to, here. I'll just learn how to use this. So how to perform Anova tests using your calculator. So kind of same place where we do all the hypothesis testing. So I'll go stat, I'll go tests, and this is going to be the last one. So once you go to test, scroll down all the way, or you can scroll up, then it's going to be option H, Anova. And when you enter, it just gives you Anova. Then you just input all the list, like L1, L2, L3, dot dot dot. Depends on how many samples we have. Okay. And when you enter, it gives you the F ratio and it gives you the p-value, and it gives you a lot more information, which we're not going to be needing. We're just going to be needing p-value. So this is what we're going to use. This is what we'll need. Okay, let's look at number 8. As a part of an experiment to see how different types of soil cover would affect slicing tomato production. Okay. This college students grew tomato plants under different soil cover conditions. Group of 3 plants each had one of the following treatment. So bare soil, commercial ground cover, plastic, straw, and compost. So I can see how there's a 1, 2, 3, 4, 5 different treatments. So I can think of this as 5 different population. And basically I want to see if there's a difference between different type of treatment or different type of population. So students recorded the weights in gram tomato produced by each one of those 15 plants. And here's the result. I'm going to change the question a little bit. We'll just test. Here, I'll make the question here. Let's test that mu1, the production for the first one, and then this. So there's no difference, means all the means are the same, all the means are the equal. Means are equal. And then, so that's going to be my H naught. So then HA is going to be, at least one is different. One pair is different. One is different. All right. So here I'm kind of inspecting the numbers, like the first one, bare one, 2,000, 2,000, 4,000, fine. But if you look at the plastic one, 6,000, 8,000, 3,000, okay. Straw one, 7, 6, 9,000. Seems like these are a little bit higher than that, right? Generally speaking. Again, this is a sample. We only have sample size 3 from each one. So we kind of have to do hypothesis testing to see for population, is there a difference? So basically what's going to happen is I'm going to put this as L1, put this under L2, put this under L3, L4, L5. So I have 5 different samples from 5 different populations. So I'll put it in there. Then what I'll do is I'll go to stat, I'll go to tests, I'll go to the last one, Anova, And then basically I'm gonna say L1, comma, L2, comma, L3, comma, L4, comma, L5. All right, so when you calculate this out, first number you get is F ratio, which I don't need. Second number you get is basically p-value, 0.0247. So 0.024 if you round off. Again, this is less than alpha. Alpha is not given, so I'm going to assume it's 0.05. That means I reject H naught. Our samples are unusual, so I reject the unusual sample, so I reject H naught. That means we're saying we support HA. So if the claim was they all have the same mean, then I'm going to reject the claim. If the claim says at least one is better or worse and it's different, then I'm going to support the claim. All right, then I'm going to have a pause and do number 9, please. And that's the end of the worksheet.